Thank Program Chair's introduction. My name is Intern Jim. I'm currently a PhD student in the Department of Computer Science and Engineering, University at Buffalo. It's my great honor to introduce my work, EarHealth. This is a collaborative work between our group and other collaborators from Northwestern University, the first affiliated hospital of USTC, and Harvard Medical School, and the University of Colorado, Denver. Sorry. As the previous presenter introduced, that in modern society, the people wear the earbuds for a long time, and the dramatically increasing of noise level, which means that more and more people are suffering from hearing loss. We can see in this figure, about 38 million people in US and 1 in 5 people worldwide suffer hearing loss. So some possible reasons include the following. The first one, is that for long-term wearing earbuds, which lead to earwax blockage and a ruptured eardrum. The second one is working in a loud noise environment, which lead to a ruptured eardrum. The third one is aged dysfunctions, which means that earwax blockage. And the fourth one is cold, flu, and allergy will lead to otitis media. I will introduce 3 common abnormal ear diseases which happened at the out part of the ear canal and the eardrum. So as a comparison, I will introduce the normal ear conditions, which means that the eardrum with normal mobility and low block in the ear canal. And for ruptured eardrum, which means there is a hole or a tear in the eardrum. And for the otitis media, which means there is some fluid behind the eardrum. And for the last one is the earwax buildup and blockage, which means there is some hardened and impacted earwax to block the ear canal. So how to detect these ear conditions? Current solutions consist of 2 parts. The first one is clinic solution. The tempometry and the otoscope can accurately detect the ear diseases, but it's uncomfortable and with high cost, and it's not portable. So there are some at-home test solutions have been proposed. The 2 devices include the Ear Check Pro and the smartphone, but the limitation is that they can only detect otitis media. So is there a more convenient and user-friendly method to detect the 3 prevalent ear diseases in daily life? So we turn our eyes to earbud computing. Yeah, as previous demo introduced, the wireless earphones, due to the low cost and convenience, are increasingly becoming a new popular wearable device. So we can see in this figure, everyone will wear at least 1 hour for earbuds in average. And on the other hand, more and more sensors are integrated into earphones, which make the earphones a personal scale human sensing platform and can provide more functions, including the music, entertainment, sport, and heartbeat, voice assistant. So how about the ear health detection? So we want to use the in-ear-based acoustic sensing to achieve this goal. As shown in this figure, the speaker will emit the acoustic signals to go through the ear canal surface and the eardrum, and then reflected to the microphone. By analysis in the reflected signals, we can distinguish different ear canal conditions. But there is a problem that people have unique ear canal structures. How to detect the different ear conditions based on their own symptoms. So, for example, for the normal and autistic media, which means that they have different eardrum mobility. And for the autistic media, ruptured eardrum and earwax blockage, which means that the ear canal structure will be different, especially for the ruptured eardrum, which means it can expand the ear canal space. So based on the introduction, we faced two research challenges. The first one is different people has unique ear canal structure to generate different echoes, and different ear conditions with different symptoms will also generate different echoes. In order to deal with the first problem, we borrowed the idea from voice conversation, which means that if we transform the input signal to a target vector, and based on the transformed signals to do the distinguish, it can improve the performance. But the problem is that we didn't know which target class we should transfer the input signal to. So we proposed and optimized the algorithm into 4 steps. The first one is use a Gaussian mixture model to represent the input signal as a sum of k multivariant Gaussian functions, and then calculate a distance matrix based on the KL. And for step 3, we choose the most similar target class based on the least distance, and then we do the transformer. On the other hand, how to recognize the inner characteristics of different ear conditions. In order to recognize the ear mobility, we use the FFT signals based on acoustic dip. The acoustic dip means that the local minimum value between 2 kilohertz and to 4 kilohertz. And the second part is based on different ear canal structures. We use the channel response features to recognize them. So the plan for this, after extracting the features, we feed the channel response feature into the neural work directly, and then we calculate some numeric features from FFT, and use a very simple neural network to distinguish different ear conditions. In experiments, we recruit 92 human subjects aged from 5 to 82, and for every subject, we collect 20 samples. For training model, we use the leave one user out because we think that for earbuds, it's a personal scale platform, so we just use one subject data for testing, as shown in this figure. And for the results, overall, more than 8% of performance showing that our system is helpful for monitoring different conditions in daily setting. But the earwax blockage just got the performance about 62, even though all the patients about earwax blockage suffer a severe symptoms. And for data transformer performance, our proposed method can be an efficient mechanism to reduce the impact of ear canal. And also, we studied different subgroups for different years. In this experiment, we asked the patient to wear one side of earbud into the ear with diseases. When 2 ears suffer the same diseases, they will wear the 2 buds. We can say the accuracy of both ears is higher because the possible reason is that the reflected signals will be strong for this one. And on the other side, we recognize based on different age subgroups. The accuracy of young people is higher because the possible reason is that along with the increasing of age, people will suffer more abnormal ear diseases, which means that it cannot be recognized so easily. And for different genders, I think the accuracy is almost the same. To further validate the stability, we recruited 4 subjects to collect the data in 5 days. And we just validate that we can extract stable features. Even though we room them in, we found that they didn't change a lot. So, which means that we can get stable features to distinguish different ear conditions. At last, we do some user experiments. We recruit 10 ear physicians and 20 normal users to ask 3 questions: the physical pain, difficulty of use, and effort. In this result, it shows that our system can get lighter physical pain and easy to be used with less time and effort. So that's all. And if you are interested in my work, please contact me and see the code part. Thank you.